Before the break, we have talked about the second type of functional linear regression models, which is the response is the function and the covariance is a scalar variable, right? So we have learned that. So now we were dealing with the third type of functional regression models. It's also the most complicated functional regression models. The response is a function and the covariance is also a function. So suppose here we have one functional covariance xiot, and we want to predict the functional response yiot. Okay, the first model we can use is we can use we call the concurrent models. So this is the concurrent models. The reason we call this as a concurrent models is because that we're using the current value of xi at the current time t to predict the value of the response at the time t, right? So we using the xi in the time t to predict the value of yi at the time t, so the same time. So therefore, we call this as a concurrent models. Okay. So to estimate the concurrent models, the ideas is very similar as to estimating the function on scalar covariance. So basically here, we will try to minimize the sum square errors, and here, because our response is a function, so we try to minimize the sum of integrated squared error, right? And define like this, okay? And then we will express beta of t as a linear combination of the basic functions, right? So we will write down the beta of t equal to c times the basic function phi, and then we can similar as the function on scalar, and then we can express the coefficient b in this form, right? Okay, so this is the estimation. We can also add in the roughing penalty on the functional coefficients beta j of t as well. Okay. So this is the first function models, concurrent models. You may think about when we're using the concurrent models, actually it has a pretty strict assumption, which is the response y only depends on the current value of x. If you think about, there actually in real applications, there can be always some delays. For example, if you think about the forest fire, right? So when we saw the forest fire, maybe that's the effect of the cumulative dryness in the forest, right? So in other words, the current value, current scale of the forest fire may depend on the dryness of the forest before the time, right? Yes. Okay. So this is a phenomenon we find in many applications. Therefore, instead of just treat the y of t only depend on the xt, at the same time, we will using these general functional linear models. So if you look at these functional linear models, we have this bivariate coefficient beta s of t, and so for this beta of s of t, it can be interpreted as the effect of the covariance at time s on the value of response y at time t, right? Okay, so now we have this bivariate coefficients beta s of t. Okay. So this is the most general linear regression model we can think about. Okay. So then, how can we estimate this beta s of t? So here is one examples for this case. So here this curve is to show the Swedish mortality data. So the y-axis is to show the log hazard rate, which is the instantaneous chance of death at each age. The age spread from 0 to 80. Okay, and so here each curve represents the log hazard at each year. Okay, so here we will treat the we kind of come with one similar like time series models. So I is the index for the year. So YIOT is the log hazard in the ith year, and yi minus 1 is the log hazard in for the I minus 1 year. So we will see how the log hazard in the year I depends on the log hazard in the year I minus 1. Okay, you can imagine this mortality rate maybe has a little shift, like now the mortality rate is lower and lower, right? With the improvement of the health and the medical treatment. So so we want to see how this change happening. So for these models, this beta s of t will represent the effect of the hazard in the year I minus 1 for the age s on the hazard rate of age t in the ith year. Okay, so this is a functional linear regression models examples. Okay. So for this one, we also doing the estimation similarly. Okay, so we will try to minimize the sum of integral of squared of these residuals. Okay, and the only thing here is that now we have a bivariate coefficient beta s of t. Okay, so the simple way to represent this bivariate coefficient beta s of t is to write this as a linear combination of the basic functions, and the basic function it will be bivariate basic functions. Okay. So basically here, we can write down beta st as the summation of cj times phi j st. Okay, so this is the bivariate bivariate basic functions. So to construct the bivariate basic functions, the easiest way we can do is to using the tensor product of the basic function in each dimension. Okay, so basically you can write down this phi j s of t as the summation. Maybe I'm using different ones. I'm using the b here. Okay. So then you can write down this as bjs of t as some like phi k of s times psi l of t. Okay, so now you will have this k l coefficients. Then you will have the double summation over k and over l. So this is how you construct these bivariate basic functions using the tensor product of two univariate basic functions. Okay. So if you do these estimations, representations, then you can see here this basis coefficients actually it's two dimension, right? So basically this coefficients can be written as a matrix of the coefficients, right? So this matrix will be the B here, okay? So B is the basic coefficients to these two-dimensional basic functions. So after we're doing these representations, so this integral is only integral with back to s, right? So then you can take the basic functions of t outside the integral, right? You can also take the b, the basis matrix outside the integral as well. So the inside will be just phi s times xis ds, right? Okay, so both phi s and xis is known, right? The basic function and the functional covariates are known. So you are able to estimate, you are able to obtain this integral numerically, right? Okay, so this is the bivariate basic function representations on the beta s of t. So in other words, here you can understand that this integral basically is a vector, right? It's a vector of a known vector, right? Depend on the basic functions and also depend on the functional covariates. So this part is known. And this phi of t is also the basic function you selected, so you also know. Okay? And then we do the estimation. The only problem here we have is that the parameter we want to estimate is the basis matrix B, right? But you can see here the basis matrix B actually is inside. It's like between phi of t and this vector, right? Yeah. So in this case, it will be very hard for you to do the estimation because generally you may realize before when we do the some minimizations, the basis coefficients will be always on the right side, right? On the right side of this second term here. Okay. So and also because of this B is a matrix, so it's hard to do the derivative with back to a matrix, right? So what we can do is instead of estimating this matrix, we can estimate this B as a vector. To do this, actually, we need to using the Cocurrent product. So how many of you have learned the Cocurrent product? Can you raise your hand? Okay. So so this is the definition of a Cronach product. So basically, if a two matrix A Cronach product with B is equivalent to each element in A multiplied by the matrix B. Okay. So in other words, if A is a M times N matrix, B is a P by Q matrix, then the Cronach product A product B will be MP times NQ matrix. Okay, so this is the definition of the Cronach product. Okay, so this is used very often when we are working on the bivariate basic functions. So if you Google Cronach product in Wikipedia, it will give you the definition of Cronach product. Okay. So for Cronach product, it has many. So this is one example of Cronach product. So basically, you will using 1 multiplied by this matrix, and 2 multiplied by this matrix, 3 by matrix, and 4 matrix. Okay. So this 2 by 2 matrix Cronach product with a 2 by 2 matrix will end up with a 4 by 4 matrix. Okay. So the Cronach product has many nice properties. So this shows the properties for the Cronach product properties. And so one thing I want to particularly emphasize is that there's two very interesting properties for the Cronach product. So one thing is that is this one. So if a Cronach product of A and B multiplied by Cronach product of C and D will be equal to C multiply C, A multiplied by C, Cronach product B multiplied by D. Okay, so this is the first property for the Cronach product. Interesting. And the second one is about the inverse. So the Cronach product of A and B inverse will be equal to the inverse, the Cronach product of inverse of each matrix. Okay, so this is very nice properties for the Cronach product. Okay, so this is interesting things. And also another thing about this is about this determinant. So the determinant of the Cronach product of A and B will be equal to the determinant of A power to M times the determinant of B to power to N. Okay, so so this formula will make the calculations much easier, right? Okay, so this is a determinant. Another properties I find it very useful is that is this one, the trace of the Cronach product of A and B will be equal to the trace of A multiplied by the trace of B. Okay. The last one we use most often is about this property. Okay. So basically, when you do, if you have three matrices multiplied together, A times X times B, if you want to, so this product of these three matrices is also a matrix, right? So when you want to vectorize this matrix, the vector of this product of these three matrices actually is equal to B transpose Cronach product A times the vector of X. Okay, so this is a very nice properties for on the Cronach product. So this is exactly the reason we introduce the Cronach product here. Is that you can see here when you do the vectorize about this matrix, you are able to move this x in the middle to the right side, right? Yes. Okay, so this is a very, very important properties. Okay, probably this is the most important properties for the Cronach product. Okay. Any questions about the Cronach product? Okay. Okay. So now let's back to our criterion. So you see here we have this actually also the vector multiplied by matrix B multiply this another vector, right? So what you can do is you can vectorize this form, okay, and then the vector of this we just learned from the property will be equal to the Cronach product of this two side, right, multiplied by vector of B, okay. So to do this way, you will firstly you will vectorize the matrix B, become a vector. So now your parameter is a vector. It's much easier when you do the derivative, okay. And also now this vector of the parameters is on the right side, so it's easy to do the derivative, okay. So the rest will be very similar as we did before, okay. So so you can find out the vectorize of the coefficient matrix will be like this, okay. So it's a little bit more complicated, involved several Cronach product, and also you can add a intercept beta 0 of t in the models, okay, and so the formula will become a little bit more complicated, okay. So you will rearrange about this x and y by these definitions, and then the estimation will be very similar. The formula will be very similar as this formula, okay. We will not go through the details. So this is the estimation. So this is the beta s of t, the bivariate coefficients. And so here, this is a counterplot of this bivariate coefficients. So basically, as we said, this beta st represents the effect of the hazard rate at age s in the previous year on the hazard rate at age t on the next year. So this is a counter plot, and it's hard to see anything here. But one thing we do find that in the diagonal area, there's a kind of plateau in this diagonal area. The length of these plateaus is roughly equal to 1. Okay. So you can imagine the hazard rate for example, age 50, in the previous year, the person will become 51 in the second year, right? So in other words, the person with age 50 will be exactly the same person as the age 51 in the next year. So in other words, the correlation of this beta s of t when s is t minus 1 is very very high, okay, because of you're talking about the same populations, okay, yeah. And also you can define the confidence interval for these parameters. So the formula will become more complicated, but the ideas is very similar as before. So basically, in the end, you will find out that so suppose the response y of t can be written as a linear combination of the basic functions. So y of t equal to cos t transpose times c. Okay. Then you can written the vectorized matrix B hat as a big matrix multiplied by the basis coefficient c. Okay, so in other words, here we will write down this big matrix before C as called a C to B map, because this matrix map the C to the B, right? So we call this as C to B map, and so the B will be equal to C to B map times the vectorize of the C. Okay. So if we have this this formula, then the variance of the B will be just equal based on the multivariate statistics. The variance of B hat will be equal to the matrix C to B map multiplied by the variance of the C. So the variance of C, suppose is this sigma, and multiplied by C to B map transpose. Okay, so this is the confidence interval on the coefficients. Okay, yeah. So this is the confidence interval for the intercept beta 0 of t, and this is the coefficients confidence interval on the bivariate coefficient beta 1 s of t. Okay, so you can see it is hard to see a big difference without a careful take careful look. Especially you don't want to have a beta s of t to be too rough, right? You will have no information there. So therefore, we will always put a roughness penalty on the beta s of t. So here, this is to show the estimation when we put the smoothing parameter on the beta s of t. So actually, for this bivariate case, the penalty actually will be more complicated. Okay. Yes, I think I need to explain to you this in more details. Okay, so let's stop here, and I will explain to you how can we control the roughness penalty on the beta s of t in next week. Okay. Yes.